Welcome back, everyone, to another deep dive. Today, we're going nuclear, well, sort of. We're diving into the world of radioactive decay.
Sounds exciting.
It is. We've got this website. It's like a gold mine for physics geeks like me, and they've got this awesome simulation applet that shows how atoms transform during radioactive decay.
A simulation, huh? That sounds like a fun way to visualize something that's usually invisible.
Yeah, it's like watching these tiny little atoms change colors over time, like a microscopic fireworks display.
So we get to see the atoms in action. Cool.
Now, radioactive decay, I know it has something to do with unstable atoms, but remind me, what's the basic idea here?
Right, so you start with these unstable atomic nuclei. We call them the parent atoms.
Parent atoms.
And they're kind of like those wobbly chairs you always try to balance on.
Oh, yeah, the ones that always seem to tip over.
Exactly. Eventually, they want to become more stable, like a nice sturdy chair with 4 legs.
So radioactive decay is like the atom's way of finding its balance?
You got it. It's the process of those unstable parent atoms transforming into more stable daughter atoms.
Okay, so the atoms are basically trying to chill out, find a more stable state, but how do they actually do that?
Well, during this transformation, the parent atom releases some energy, and that can involve throwing off different types of particles. Those particles are what we call alpha, beta, and gamma radiation.
So like the atom is shedding some extra baggage to become more stable?
Exactly. It's like a cosmic weight loss program.
Yeah.
Now, this specific simulation we're looking at focuses on something called a 3-state decay chain.
Three-state, like a relay race for atoms.
You got it. Instead of just one transformation, it's a chain reaction. The parent decays into a daughter, but the daughter is still a bit unstable. So it needs to decay further into a granddaughter atom. The granddaughter is stable.
So it's like a whole family saga playing out at the atomic level.
That's a great way to put it. And the simulation uses colors to help you keep track of all the players. Red for the parent, blue for the daughter, and gray for the final stable granddaughter.
So we actually get to see those red atoms turn blue and then finally settle down as gray.
You got it. And you can see how the number of each type of atom changes over time.
I'm already getting hooked on this. Now, you mentioned something earlier about half-life. What exactly does that mean in this context?
Right, half-life. Imagine you've got a pizza.
Pizza. I'm listening.
You cut it in half, and cut that half in half again, and so on. Half-life is the time it takes for half of the atoms of a particular type to decay. And each stage in the decay chain, parent to daughter, daughter to granddaughter, they each have their own unique half-life.
So some atoms are quick to decay, while others take their sweet time.
Exactly. And that's what's cool about the simulation. Instead of just trying to imagine it in your head, you can actually see how the different half-lives affect the speed of those color changes.
You know, seeing it visually must make it so much easier to grasp, like watching a complex dance unfold right before your eyes.
I agree. And speaking of complex, the website also has all the math behind this decay process. They've got the equations that predict how many atoms of each type will be left at a certain time.
Equations, huh? Well, math and we have a bit of a love-hate relationship.
I hear you. But honestly, you don't need to get bogged down on the specific equations to understand what's going on. The key is to focus on the relationships, how the number of atoms, time, and half-life are all connected.
All right, so the map is there if you want to dig into it. But how does this 3-state decay actually play out in the real world? Any examples?
Great question. Think uranium, the element they use in nuclear power.
Uranium. Okay, that rings a bell.
Uranium goes through a whole cascade of decays before it finally ends up as a stable lead isotope. It's like a multi-generational saga.
Wait, so the same process that powers our cities is happening naturally in rocks and stuff?
Precisely. And this process isn't just about energy. It's also crucial for figuring out the age of ancient rocks, fossils, even the Earth itself.
Whoa, hold on. So by understanding how uranium decays, we can literally look back in time.
You got it. Radioactive decay is like a clock that lets us trace history billions of years back. Pretty cool, right?
Definitely cool. I'm starting to see how this seemingly simple process has some pretty huge implications. But there's something else I remember, something about differential equations.
Ah, yes, you're remembering correctly. Those equations are called Ordinary Differential Equations, or ODEs for short.
ODs. Oh, okay, that sounds a bit intimidating.
They might sound scary, but really they're just tools to understand how things change. In this case, they describe how quickly those red atoms are disappearing and how fast the blue and gray ones are appearing.
So the simulation is like a visual representation of these equations in action.
Exactly. It's like a visual solution to some pretty heavy-duty math.
Now that's impressive. So it's not just a cool animation, it's based on some real science. And you mentioned we can even play around with the simulation ourselves.
Uh, Absolutely. You can adjust the half-lives for each stage of the decay and see what happens. You can make the parent decay really quickly, but give the daughter a long half-life.
So, like a super fast runner passing the baton to a much slower one in a relay race.
Exactly. And you can see how that affects the whole decay process, how those red, blue, and gray populations change.
That sounds like a great way to get a hands-on understanding of these concepts. Are there any other resources on that website I should check out?
Definitely. They have other simulations, some focusing on simpler two-state decay, and even interactive visualizations using other tools.
It sounds like a playground for physics enthusiasts.
It is.
Yeah.
They've even got links to more in-depth explanations if you really want to dive into the nitty-gritty.
I'm definitely bookmarking this site. I'm already feeling inspired to explore more. This whole concept of radioactive decay, it's like we're peering behind the curtain of the universe, seeing how the tiniest pieces work.
It is pretty mind-blowing when you think about it, and it makes you wonder, what if we could control this process? What if we could speed it up or slow it down?
Whoa, control radioactive decay. Now that's a thought. What would that even look like? What could we do with that kind of power?
That's a question for our next deep dive.
Controlling radioactive decay, huh? That sounds like something straight out of science fiction. Is that even remotely possible?
It might sound like sci-fi, but it's a question that scientists are actively exploring. Right now, we're pretty much at the mercy of natural decay rates.
So, like, uranium just decays at its own pace, and there's nothing we can do about it.
Well, it's not quite that simple. We can influence the rate of decay a little bit in certain situations.
Really? How?
For example, extreme conditions, like really high temperatures or pressures, can actually affect decay rates slightly.
So we can nudge it a little, but we can't really control it precisely.
Yeah, that's the challenge. But imagine if we could. Think about being able to speed up the decay of nuclear waste, making it safe much faster, or slowing down the decay of medical isotopes so they last longer.
Okay, I'm starting to see where you're going with this. It's like having a volume knob for radioactive decay. But how would we even begin to control something that seems so fundamental to how atoms work?
That's the big question, and scientists are exploring all sorts of possibilities. One really interesting area of research is using lasers.
Lasers, like something out of Star Wars.
Kind of. The idea is to use lasers to manipulate the energy states of atoms, which could potentially affect their decay rates.
So high-tech solutions for a tiny problem.
Exactly. And it's not just lasers. Researchers are also looking into the role of the environment around the atom, things like specific materials or magnetic fields.
So we're basically trying to figure out how to speak the language of atoms, how to influence their behavior.
I like that analogy. It's like learning a new language. It takes time, a lot of experimentation, and hopefully some breakthroughs along the way.
You mentioned the implications for nuclear waste and medical isotopes. Can you unpack those a little more? What would controlling decay actually look like in those fields?
Sure. Let's start with nuclear waste. One of the biggest problems is its long-lasting radioactivity. Some of the byproducts of nuclear power can stay dangerous for a really, really long time.
Thousands of years, right. I remember learning about that. It's a major headache for figuring out how to store it safely.
Exactly. But what if we could speed up that decay process? We could potentially transform that dangerous waste into something much safer and in a much shorter time frame.
Now, that would be a game changer for the nuclear industry. It could make nuclear power much more appealing as a clean energy source.
Absolutely. And then there's the medical side. Think about being able to fine-tune the decay rate of the radioactive isotopes used in cancer treatments.
So instead of just blasting the tumor with radiation, we could adjust it based on the patient's specific needs.
Exactly. You could target tumors more effectively, do less damage to the surrounding healthy tissue, and maybe even personalize those radiation therapies.
It sounds like a win-win for cancer patients. Less risk, more effective treatment.
This is amazing. It seems like controlling radioactive decay could have a huge impact on so many different fields.
And we haven't even touched on space exploration. Imagine a spacecraft with a power source based on controlled radioactive decay. It could provide constant energy for years, even decades, without needing to refuel.
That would be incredible. We could send probes to the far reaches of the solar system and beyond, no problem.
It's an exciting possibility for sure. And even though controlling radioactive decay might seem like a distant dream right now, the potential benefits are so huge that it's a scientific challenge worth pursuing.
I'm completely with you on that. This whole topic is just blowing my mind. It's amazing how something as seemingly basic as atoms decaying could hold so much potential for the future.
It really speaks to the power of scientific curiosity and that constant drive to understand how things work.
Well said. But, we've been focusing on the big picture for a while now. Let's zoom back in on that simulation for a moment.
Sure, what did you want to talk about? What are some specific things our listeners can try out with that three-state decay simulation we were talking about?
Well, as I mentioned earlier, one thing you can do is play around with those half-lives. Change the half-life of the parent, then the daughter, see what happens when you mix things up.
So you could have the parent atom decay super fast, but then the daughter takes its sweet time.
Yeah, exactly. And you'll see how that affects the whole process of how those red, blue, and gray atoms change over time.
It's like a hands-on way to learn about those concepts, to see how it all works in action.
Exactly. It's all about exploring. Another thing you can do is look at what the simulation calls the activity of the sample, which basically tells you how many decays are happening at any given time.
So that's like a measure of how radioactive the sample is at any moment.
You got it. And you can see how that activity changes as the atoms decay until it eventually reaches what we call a state of equilibrium.
Equilibrium. So things have balanced out and the decay rate has settled down.
Exactly. And the website also has some really interesting questions to get you thinking as you play with the simulation.
Ooh, I love a good challenge. What kind of questions?
For example, it asks you to think about what happens to the total number of atoms in the system over time. Does it stay the same? Does it increase? Or does it decrease?
That's a good one. I'll have to try it out and see if I can figure it out.
It's a great way to really test your understanding of how it all works. And the website also points out some of the limitations of the simulation, which is important to keep in mind.
Limitations, you mean it's not perfect?
Well, no simulation is perfect. For example, this simulation assumes that all the atoms are identical and that they decay independently of each other.
But in the real world, wouldn't there be some differences between atoms? And wouldn't they interact with each other too?
Absolutely. The real world is always way more complex than any simulation can capture perfectly.
Right. So it's a great tool for visualizing and understanding the basic concepts, but we have to remember that it's a simplified version of reality.
Exactly. It's a starting point for exploration and critical thinking, not the final answer.
Well, this has been a mind-blowing conversation. I'm definitely feeling a lot more knowledgeable about radioactive decay now. Who knew something that happens at such a tiny scale could have such huge implications?
It's pretty amazing when you think about it. It really highlights the power of scientific inquiry.
Absolutely. But we've talked a lot about the positive potential of controlling radioactive decay. Are there any downsides or risks we need to consider? Could this technology be misused?
That's a really important question, and it's one that scientists and ethicists are grappling with right now. Any new technology, no matter how promising, can be used for good or for bad.
It's kind of a double-edged sword, right?
Yeah, exactly. I mean, think about the example of nuclear waste again. Being able to speed up its decay, that would be huge for the environment, make things much safer.
Yeah, it would be a total game changer.
Right. But what if that technology fell into the wrong hands?
You mean someone could use it to make even more dangerous stuff?
That's the risk. The same knowledge that could be used to solve a problem can also be used to create new ones, unfortunately.
It's a bit of a scary thought.
Yeah, it is. It's like we're at this crossroads, We've got this incredible power, but we have to be really careful about how we use it.
You're right. It's a huge responsibility.
Definitely. And that's why it's so important to have these conversations, to think about the ethical implications alongside the scientific advancements.
Absolutely. We can't just blindly rush ahead without considering the potential consequences.
It's not just about can we do it, but should we do it, right?
Exactly. So any thoughts on how we can navigate this, make sure we're using this knowledge responsibly?
I think it really comes down to collaboration and communication. Scientists need to be talking to policymakers, to ethicists, to the public. We need to have open and honest conversations about the potential risks and benefits.
It sounds like we need a multi-pronged approach, not just focusing on the science itself.
Yeah, I think that's key. And it's not just the responsibility of scientists either. Everyone has a role to play in shaping how these technologies are developed and used.
Well, this has been a truly eye-opening deep dive. We started with these tiny atoms, and now we're talking about the future of humanity. From powering our cities to fighting diseases and exploring space, the implications of radioactive decay are just mind-blowing.
It's a testament to how interconnected everything is, isn't it?
Absolutely. But as we wrap up, any final thoughts for our listeners?
Well, I'd say the biggest takeaway for me is that radioactive decay, it's not just some abstract concept in a textbook. It's a fundamental process happening all around us, constantly shaping the world we live in.
Yeah, it's in the air we breathe, the ground beneath our feet, even our own bodies.
Exactly. And understanding how it works is essential if we want to harness its power for good to solve some of the biggest challenges we face as a species.
It's about responsible innovation, making sure that our pursuit of knowledge ultimately benefits humanity.
I couldn't have said it better myself.
Well, on that note, a huge thank you to our expert for joining us today and sharing your insights. And to our listeners, thank you for tuning in to another deep dive.
It's been a pleasure.
Keep those brains buzzing, folks. Until next time, happy exploring.